This is my TMS 9900 based homebrew that we've been building up over the last couple of episodes, and I think it's coming out looking absolutely beautiful. But the CPU in this was actually lifted straight out of one of these. This is a TI-99 home computer, and I don't know, I have a soft spot for these. I just really like this thing, and I think it's a great retro computer to get into. But it did have a bit of a reputation for being a little bit of a dog in the home computer world. But the CPU in this, the TMS 9900, I think is one of the most powerful CPUs you could have gotten in a home computer in the early 1980s. It is effectively a full-fledged 16-bit mini computer CPU crammed into a home computer. So if you've got this absolute powerhouse of a processor, how is it that the TI-99 ended up so slow? Well, that 16-bit CPU was shoehorned into an 8-bit system, which meant that the data bus had to be multiplexed down. And all of the system memory was gated away behind the video display processor, which meant that the CPU couldn't really do what it was good at. And what it's good at is 16-bit operations, multi-user capability, and big storage. All three of those are the strengths of the CPU, and not a single one is used in the TI-99, which is just a crying shame. So we ripped the CPU out, and we're building up this homebrew to kind of lean on to some of those features that the TI-99 didn't make use of. So this thing should be pretty exciting, and so far we've got it set up with 2 kilowords of ROM as well as 6 kilowords of static RAM. Now we can push that out a lot farther, but I think for the time being 6 kilowords is going to do just fine, which raises the question of what is the actual goal of this homebrew? Well, if we're going to talk about goals, we got to talk about software. And a lot of people have recommended to me to build out the homebrew computer to be able to run BASIC. And I think this is an excellent litmus test for the capability of a homebrew computer, but much to the chagrin of my good friend Corey over at gotbasic.com, I'm not going to do that. I have a ton of machines in here that can run very different versions of BASIC, and I want to do something a little bit different with this homebrew. I want to run some Bendix G15 software on it. Notably, I want to port Intercom 1000 to TMS 9900 assembly. Now, Intercom 1000 was written for the Bendix G15, a full-fledged vacuum tube computer from 1956. And it's an incredibly interesting high-level programming language because you interact with it using only numeric symbols, 0 through 9. Now, that's not going to be an easy task, but our hardware is more than capable of it because Intercom 1000 was designed to fit in the incredibly limited memory space available on the Bendix G15. Effectively, the entire program fits in less than 1,000 words of memory. That is amazing, which means that we could theoretically store the entire program in ROM. But one more trick that I want to do to it is I want to tweak it ever so slightly to make it multi-user, at which point we may not be able to stuff it all in ROM, and I don't particularly want to stuff it all in ROM anyways because I really want to load it in via some kind of external medium. Whenever the machine is first powered on, I want the user to be greeted with a menu. The first option on that menu would be to go to something like WASMON, a memory monitor that allows the user to view and change the data values at specific addresses in memory, and then jump to those addresses and start executing from there. The second option would be to go to a specific location in ROM that contains a bootloader that will then start loading in a program from some kind of external storage, copy that into memory, and then start executing it. And for that, I'm thinking that we're going to use a little audio cassette tape that you saw so often on machines from the early 1980s. So to get to that goal, all we're missing is some kind of serial communication with the outside world. And for that, we're going to have 3 serial ports. The first is going to be for the console terminal that the main user interacts with. The second is going to be an expansion RS-232 port for a second terminal for multi-user applications. And the third is going to be dedicated solely for communication to that magnetic tape unit. So our goal and the final shape of the machine is starting to coalesce, which means it's time to start thinking about the actual physical construction of the machine. and it hit me like a flash. The entire thing is going to be based completely around this little guy right here. This is a TI Insight data terminal, and this is going to be the console terminal. I want to build a little tower that sits below this that contains all of these circuit boards and the MagTape drive. And ultimately, I want to start working on designing the UART that's going to communicate with this data terminal. Now that's going to be incredibly complex, and we're definitely not going to get to all of that today, but I really want to start focusing on the transmit side first, because then I can write a little program that lives in ROM that transmits something over and over and over to the data terminal here, and we might be able to see this thing print Hellorld on this data terminal today. The first step is to remove the original power supplies. These were way overkill and originally just a temporary solution until we had an idea of what shape the build was ultimately going to take. I have some new supplies that will work much better, but first, with the old supplies out of the way, I need to remove the DC distribution PCB. Then I need to start measuring things out. Each backplane holds 4 cards, and on the right side here, I want there to be 3 backplanes for a total of 12 cards. That'll hold the computer and 2 of the serial ports. On the left side will be the tape drive and the backplanes for controlling that. Overall, the board that holds the backplanes and the tape drive will be 32 centimeters wide, and the rails add an extra 2.5 centimeters to that. If I check the width of the data terminal, that comes out to 35 centimeters wide. This, I think, is going to work out absolutely perfectly. These rails I found at the local hardware store, and they're a little overkill, but it's what they had in stock. They're also the shortest rails I could find at 16 inches or 40 centimeters, so our computer footprint is going to be almost perfectly square at 40 centimeters by 40 centimeters. I'll run the board through the table saw and then trim it down with the radial arm saw, and once I'm happy with the size, it's time to drill some pilot holes in the side. Then screw in the sliders for the rails. Since this is wood, I'm using 4 screws per slider, which should keep everything nice and sturdy, and giving it a test slide, yeah, that's gonna be perfect. Next, I need to figure out just how high to make the side pieces. So with the bottom all together now, I slotted a card in and took a measurement. Doing a little bit of simple addition here, I need 16 centimeters from the bottom to the base of the top piece. The wood thickness for the top piece is 2 centimeters, and then I want a 3 centimeter lip to keep the terminal from sliding off the side. In total, that means that I need 2 side pieces that are 21 centimeters by 40 centimeters. I'll go grab another piece of scrap plywood, make my measurement marks, then run it through the table saw and get my pieces. Setting them in place, and yeah, that's gonna do it. The first step is screwing the other half of the sliders onto the side pieces. Again, I used 4 screws per slider, and I actually spaced these out by about 2 centimeters using washers between the slider and the side panel. Sliding them back together is so satisfying, and this is really shaping up like I was envisioning in my head. To mount the top piece that the terminal sits on, I'm going to use these little plastic L brackets I had laying around from a previous project. The terminal is pretty lightweight, so these should be more than plenty strong enough. And that's pretty much it for the case build for now. Flipping it over, I'll slot the baseboard with the cards and backplanes mounted in, then I'll set the terminal on top, and that's just perfect. Even the puppy agrees that this is pretty awesome looking. Next, let's get the new power supplies mounted, and for that, I'm going to use just these 2 supplies. I need 4 voltages in total, and these will get that done. The larger supply outputs plus 5 volts at 5 amps, plus 12 volts at 2.8 amps, and minus 12 volts at 0.5 amps. The smaller supply will be used to get negative 5 volts at a way overkill 5 amps. Let's get these things mounted, and since space is at a premium, I'm thinking standing on their sides like this is going to be the most compact. The big supply is easy to mount. I'll just screw it down through the mounting holes on the side of it. The smaller supply, though, required that I make this little mounting bracket. Once I've got the bracket in place, I'll pull the bigger supply out and get the smaller supply securely mounted before remounting the bigger supply. Next comes the wiring. I need to put a switch on the AC live side, and for that I'll actually just use a light switch. They're incredibly reliable and meant for switching AC. So with the power switch now mounted and all the AC run, it's time to run the DC over to our DC distribution board. After spending about 3 hours routing cables in as clean a manner as I could, let's give it a quick test. And we have negative 5.06 volts, negative 12.00 volts, that's nice, plus 11.66 volts, which is a little low, but that should be all right, and plus 5.076 volts, which is perfect. Let's get all the cards plugged in and give this thing a quick test. I'll bring the main chassis over and set it on the table. Then I'll slide in the board that holds all the cards, flip the power switch, and nothing went up in smoke, and the lights seem to be doing the right thing. This turned out looking absolutely beautiful. I've been calling it my mini computer because it apes all the design cues of the bigger machines, but it's about 1/4 to 1/5 of the size. My buddy TechAV said it kind of looks like a cash register, only the drawer is for the computer and not cash, which I find both completely accurate and absolutely hilarious. So that's one major milestone finished today. And yes, the wood is unfinished and we can make plywood look pretty good, but ultimately I think what we're going to do is we're going to use this as a template for building a case out of proper real deal stuff, maybe teak or oak or something, make it look like a real nice piece of furniture. And I'm gonna lean on my buddy Corey over at gotbasic.com for that because he's a little bit of a woodworker and we've been itching for a project to do together, so this is gonna be it. So with that goal out of the way for today, what about the next goal, which is trying to get this thing to print something over one of the serial ports that don't exist? And that leads us to this giant mess of wires right here in front of it. And well, let's rewind a little bit here. In the previous episodes, I was able to sit down and show a schematic and then cut out a PCB and get that plugged in because I had done all of the prototyping work like 6 months before I even ever started filming. But my prototyping only went up to the point that we got in the previous episode. I never prototyped out the UARTs. This is completely new territory for me. So it actually took about 2 to 3 days of fiddling with this thing. And well, check it out. Here's the result. If I flip the power switch here, how cool is that? It's printing Hellorld over and over and over again. It seems like such a simple thing, but this was a colossal amount of work to get it to this point. But this is a pretty neat magic trick I pulled off here. So how did I do it? Well, there's 2 big things at play here. There's the actual circuit right here that contains the UART and all of the decoding logic for that. And then there's the code that I had to write that we burned into the ROMs that the CPU is executing. So let's break both of those down and take a look at them in more detail. The main party piece on here is going to be the UART, which stands for Universal Asynchronous Receiver Transmitter. And the one that I'm using in this case is the TR1602B. Now, a lot of people are going to probably bemoan my choice of UART on here because the TMS 9901 actually interfaces with the CRU of the TMS 9900 on here. But like, I like the TR1602. It's used in the ADM. I think it's a really neat chip and I wanted to build something with it. So that's why I chose it, because it struck my fancy. And honestly, there's no better reason to do something than it strikes your fancy. So if we want to get this 1602 hooked up correctly, we got to look at the documentation here. And I got the datasheet right here. Pins 1, 2, and 3 are for voltage supplies. Pins 4 through 12 is all for receive. We're not doing anything with that today, so we're going to ignore that. Pins 13, 14, 15 are for parity framing and overrun errors. Again, we don't particularly care about that. Pin 16 is a status flag disconnect. We do actually need this to read the THRE signal. Pin 17 is the receiver register clock. This is the baud rate. This is going to be the same as our transmitter register clock, and we're going to set that to 300 baud. Pin 18, 19, and 20 have to do with receive, so we're going to ignore that. Pin 21 is master reset. Pin 22 is the transmitter holding register empty, or THRE signal. This is a pretty vital signal to us because it lets us know that the UART has finished transmitting a character out and it's ready for the next one. The CPU is ticking along at 3 megahertz, and so it can way overflow the paltry 300 baud that we're going to have this UART spewing characters out at. So we need a signal from the UART to say, hey, I'm ready for the next character. Pin 23 is transmitter holding register load. We strobe this to tell the UART to grab whatever value is on the data bus, and send that over to the transmitter register to transmit out. So this is also an extremely vital signal to us. Pin 24 is transmitter register empty. This is slightly different than transmitter holder register empty, and honestly, like, it seems awfully weird that you have both of these. For our purposes, we can just ignore pin 24 here. Pin 25 is transmitter register output. This is our serial data out. And then pin 26 through 33 is going to be the 8-bit data value that we read in whenever we strobe THRL. Pin 34 is a control register load. We just tie this perpetually high. Pin 35 is parity inhibit. We're going to tie this high so that we have no parity going on. Pin 36 is the stop bit select. We're going to tie this one low so we have one stop bit. Pins 37 and 38 are the word length select. We're going to tie both of these high because we want 8 bits. Finally, pin 39 we don't particularly care about. So there you go, 40 pins on the UART, and if all you're doing is transmit, it's pretty easy to set up. But if you have just the UART, that's not quite enough, as you can tell by the rest of the circuitry on here. And interestingly, I have a pretty large ROM on here. This is a 28C64, but ultimately I'm going to end up using a 27C16, a little EEPROM down here. I'm just using the 28C64 for now, so that way I can flash it rapidly. And I'm using this to essentially consolidate a bunch of memory mapped I/O logic into one single IC. So if we look at the schematic here, we can see that on the UART we have all of the pins tied high and low that we needed to tie high and low. And then the TR1 through TR8 is just tied directly up to data bus 0 through data bus 7. Then for our clock, instead of using a crystal oscillator, because this is going to be at 300 baud because that's the only speed that this terminal can go at, I'm just using a 555 timer and then buffering it through an OR gate over to the UART over there. Where it gets really interesting is our ROM up here. You can see that we have 15 address bits, and the 4 highest address bits are going through a pair of NAND gates that then go through an OR gate that ultimately go to the output enable. This means that this ROM is disabled for any address below F000. So we have like 2K of MMIO, which is way too much, but we've got a pretty wide address space that we can work with here, so might as well make life easy on me here. The remaining address pins for the ROM then just go straight to the rest of the address bus there. And so THRL just goes straight into the UART. THRE is going to go to a NAND gate that is shared with the THRE signal coming out of the UART. And then this goes into a little NPN transistor that I'm using in open collector mode. So that way the CPU can just check that data bus line at that specific memory address, and we can tell if the transmitter holding register is empty or not. The final thing that we're doing is right up here on the top, where we take the transmitter register out. We're buffering it through a little OR gate here, and we're sending that into a PNP transistor that is going between +5 and -12 volts. This is creating the RS-232 levels that we need to send it over to here. And then the output from that is like literally just going straight to the data terminal, printing Hellorld over and over and over again. So it seems like a pretty simple schematic, but remember, this is only for transmit. This is going to get much more complex when we get into receive. But even if you have this, that doesn't actually end up printing anything on here unless you write the correct assembly program in TMS 9900 assembly to run on the computer. And now we're getting into some pretty tricky assembly. We're going to start with an RORG that tells the assembler where these following values are going to be placed in memory. And we're starting at 0000, and we're going to place the value of 1000. This is the workspace pointer, so that's where all of our registers are going to live. And then we follow that up with a value of 0080, which is the start of the program. And you can see the very next instruction is RORG 0080. So we start with an LI, or load immediate, register 2 with the value of 0 to 100. Then we're going to do a load immediate register 3 with the value of F000, and load immediate register 4 with F002. 0200 is where all of the ASCII data that we're going to print out is. And you can actually see that at the bottom here, where I have RORG 0200, and then I have a bunch of data, 0048, 0045, 004C. Now, it is a bit wasteful to do it this way because I'm not utilizing both bytes of our 16-bit word, but this was the simplest, most pain-free way that I could think of. And at this point in time, we're not trying to write beautiful code. We're trying to write functional code that makes it easy to troubleshoot the prototyping hardware, because I made a lot of mistakes when I was trying to figure that out. Then F000 and F002, these are going to be our two MMIO addresses that the ROM on the hardware here is going to decode. And now we're getting into the real meat and potatoes of the program. We're going to start with a move *3, *1. *3 here is pretty tricky because this says to use the value stored in register 3 as a pointer to a location in memory to grab the actual value that we care about. So R3 in this case is storing F000. So we want to actually grab the value that's at that specific memory location and store it into register R1. And F000 is our MMIO address for THRE, letting us know if the transmitter holding register is empty. But this hardware is only touching data bus bit 0. It's not touching any of the other 15 bits. And so we really only care about data bus bit 0. So we need to do an AND immediate of register 1 with the value of 0001. This makes all of the remaining 15 bits 0 and then just allows whatever value is in data bit 0 to pass through. After that, we do a JEQ, jump if equal to 0. Whenever you do a move or a logic operation or an arithmetic operation, pretty much anything that involves the ALU, it updates all of the status flags in the CPU. And one of those status flags is it compares whatever value just moved through the CPU with 0. And if it's equal to 0, it kicks off that status flag. So then we can test that status flag. And so if the status flag is saying that it's equal to 0, we're going to jump back up to PR1 and we're going to run this whole loop again. This is our tight loop that's checking to see if the UART has transmitted its data out. If the UART has transmitted its data out, we're going to move on to the next instruction here, which is move *2, *1. And so we're going to load register 1 with the value pointed at by 2, and 2 is pointing to 0200, and this is going to be our first letter of ASCII, which is the H. So we want to do a move 1, *4, which says move the contents of register 1 into the location pointed at by register 4. So we're going to put register 1 onto the data bus, and we're going to put the contents of register 4 onto the address bus. And because this hardware knows to listen to that address bus, it's going to kick off a signal that tells the UART to grab the value off of the data bus and start transmitting it out. Now, while that's transmitting it out, we have one more test that we want to do in our assembly to check to see if we've printed absolutely everything. And so we're going to do an increment R2 by a word. So R2 was originally storing 0200. We're going to bump that up to 0202. And then we're going to move the value at 0202 into register R1. And then we're going to check if that is equal to 0. And if it is equal to 0, we're going to jump back up to the top and we're going to run this whole thing all the way over again. But if it's not equal to 0, we're just going to jump back up to PR1 and print out the next character. And then the entire program runs on a tight loop over and over and over again forever, which you can see it doing absolutely perfectly right now. It's been doing this for like over an hour. This is so cool. Like, this is super exciting, y'all. We have built a capable homebrew computer, but also this proves a couple of things. It proves that our UART design is coming along very nicely. Even though we've only done the transmitter side of it, we've set the perfect foundation here for building out the receiver side of it, which is something that we're going to do in the next episode. But also this proves that my PCB design here is going to be totally fine. A lot of people left comments in the previous episodes saying that my backplane design and my big swoopy curvy traces absolutely would not work at 3 megahertz, but that's pretty complex code working absolutely flawlessly to print it out. Like, this is gonna work. Like, absolutely. This is so cool, man. I'm super excited here. So in the next episode, we're going to get into the receiver side of this UART. So that way, whenever I type a key up here, maybe we can have it echo back and I can start using this as just a really complex typewriter. But that opens the door for doing some really fun stuff like writing WASMON or a memory monitor for this thing. So I want to thank you guys so much for hanging out with me today. And I hope to see you in the next one.